Hello, we continue this lecture on successive differentiation by getting back to the very first example that we took, x to the power of m, and writing that m does not belong to the set of natural numbers. Let us say m is something like p by q, where p and q are integers, positive integers, and of course q is not equal to 0. Now, in such a situation, one can keep on differentiating x to the power of m without landing up into any problem. And of course, we can write with y is equal to x to the power of m, y1 is, as we did earlier, m x m minus 1, y2 is m minus 1 x m minus 2, and so on. Y sub n is m minus 1, m minus 2, m minus n plus 1, and x to the power of m minus n. So, if we were to take the sixth derivative of, say, x to the power of half, we just keep on replacing m by half, half minus 1, half minus 2, and evaluate the terms up to n will be 6. So, m minus 5 is the last term, half minus 5. So, that is a bit of numerical calculation, but the focus is on the statement that when m is a positive integer, this deriving process will come to an end after a finite number of steps, whereas if it is of the form 1 by 2 or 4 by 3 or whatever, then the function can be derived as many times as one wishes. 20th derivative, 27th derivative, 13th derivative is not a problem at all. We now go to another class of problems, another class of expressions. Let us say we wish to find the nth derivative of a function like this. So, we take, let y be equal to 1 over ax plus b, and what do we need? We want to find y sub n. Now, clearly we can write y1 is equal to, if we can notice that this is ax plus b, we'll write that before we do y1. So, we write this y is equal to ax plus b to the power of minus 1. So, that implies y1, the first derivative is minus 1 ax plus b minus 2, and applying the chain rule, there will be a factor of a. So, the first derivative is minus 1 to the power of 1 ax plus b to the power of minus 2 into a. This is applying the chain rule, differential coefficient of ax plus b is plus a. Carry on one more step. We say y2 is equal to minus 1 minus 2 ax plus b minus 3 a square. So, this we write as minus 1 to the power of 2 into 1 into 2 ax plus b minus 2 minus 1 a to the power of 2. See, the arrangement of these terms is very important so that one can build up immediately a form in the mind, the nth derivative form in the mind straight away. What is being suggested is very simple. We will infer from here, or perhaps we can do one more differentiation. This implies y sub 3 is equal to minus 1 once again. So this will become minus 1 to the power of 3, because this is 1 and there will be a minus term coming. Then 1, 2, 3, ax plus b minus 3 minus 1 and a to the power of 3. Not 9 to the power of 3, it's a to the power of 3. So what is being suggested is very simple, that if we were to carry on this derivation process, we would land with something like, if I rub out this part, which does not harm us at all, then we can write from here and infer that this implies y sub n is equal to minus 1 to the power of n. This is factorial 3. Here we will get factorial n. Ax plus b, now when this is y3, it is minus 3 minus 1. So when it is n minus 1, and there will be as many a's as factors as the order of differentiation. In other words, we will simplify this and write it as this is equal to minus 1 to the power of n factorial ax plus b. We'll put it down, n factorial a to the power of n and ax plus b to the power of n plus 1. That's it. So minus 1 to the power of n factorial a to the power of n and ax plus b to the power of n plus 1, not n. So if one were to derive, for example, the fifth derivative, I mean, a problem can be taken straight away. Find y5 for fx is equal to 1 over 2x plus 3. We will just substitute here. N is 5. So we write y5 is equal to minus 1 to the power of 5, n. n factorial is 5 factorial. A to the power of n, this is ax plus b, so a is 2. 2 to the power of 5, a to the power of n, divided by 2x plus 3 to the power of 6, 5 plus 1. So that is the fifth derivative of 1 over 2x plus 3. One can check this directly, but it's not necessary because we've come from a general formula to a particular formula. This result we will need separately, so I'm just capturing this here or maybe in one corner. We'll capture this result in one corner, because in the next one that I'm going to do, this will come in handy. So y is equal to 1 over ax plus b implies y sub n is equal to minus to the power of n a to the power of n factorial and a to the power of n. Divided by ax plus b. We will now use this particular result which we have just written down, and I will show you why I have written this down. Because the next problem I have put up on board is find y sub n for y is equal to log ax plus b. I repeat the problem. Find y sub n for y is equal to log base e ax plus b. We will see how the solution of this depends on that formula. Now, I have written down that if y is equal to this, then y sub 1, the first derivative, is 1 over ax plus b into, apply the chain rule, a. That means a over ax plus b, which I have written as a into 1 over ax plus b. Now, the next point is very, very significant and to be understood very clearly. We have started with y as this one. We want to derive this function n times. We have carried out one derivation and got it to this form, subject to, of course, a presence of one factor a. What I am trying to say is very simple. If I have to start here and derive n times, and if I have done one derivation directly, then from here, if I derive this, if I differentiate this n minus 1 times, not n times, then from the beginning to the end, I have differentiated exactly n times. I repeat once again, I have to differentiate n times from here. I have done one direct differentiation. So, what remains is from here, I will derive this or differentiate this n minus 1 times. So, we will have to do nothing, put an a and straight away use this formula and replace every n there with n minus 1. So, I will use that and the force of that and the power of that to conclude that y sub n is equal to a 1 over ax plus b derived n minus 1 times. In other words, I will take this formula and replace every n by n minus 1. So, this would be, the a remains minus to the power of minus 1 to the power of n minus 1, that is fine. N factorial becomes n minus 1 factorial, that is also fine. A to the power of n becomes a to the power of n minus 1. There is an a outside, and down below we have ax plus b to the power of n. So, ax plus b to the power of n. The net result is, if I can just rub out a little bit from here, the net result is, from here we go up and write a to the power of n minus to the power of n minus 1, n minus 1 factorial, n minus 1 factorial, yes, there we are, and ax plus b to the power of n. There we are. So, this is the nth derivative of log base e ax plus b, and it depended on our earlier work on the derivative, n derivative of 1 over ax plus b.